All right. So let's get started. We're going to finish up our titration discussion here. We talked about how our titration curve has these four regions. And last class for a weak acid, strong base, we got through three of them, ending at the equivalence point. Remember, the equivalence point is when there is exactly as much acid that you initially started out with, moles, as you have moles of base added, right? So if all of our weak acid has reacted with our strong base, that means that now at the equivalence point, we're left with a solution of, what are we left with? Let's look at our balanced chemical equation that we came up with here. Oh, that's not it. Well, we had our weak acid reacting with our strong base. Okay, that produces our conjugate base and our water. If all of this has reacted with all of this, what am I left with a solution of? This weak base right here, right? That's all I have at the equivalence point is now just a flask full of weak base at the equivalence point. And so when we calculated our pH to determine the pH, we just applied what we know about calculating pH for a weak base, which is what we learned in chapter 17. All right? So in our three regions here, for a weak acid, strong base titration, before any titrant was added, all we have is a flask of weak acid. So we calculated our pH like we learned how to do for a weak acid in chapter 17. All right. Between our initial point and our equivalence point, we have this mixture of weak acid, weak base, which we call a buffer. And we know how to calculate the pH of a buffer using the Henderson-Hasselbalch equation. At the equivalence point, all that weak acid has reacted, and all I'm left with is that weak base. And so I calculate the pH of my equivalence point, just like we learned how to do for a weak base in chapter 17. All right, so now we have our last region to go over here, which is after the equivalence point. So now I've added not only enough base to react with my weak acid, but now I'm even past that. I've added even more strong base to this mixture. How do I calculate the pH? Okay, so our last problem here. What is the pH after 100 milliliters of our 2.5 molar NaOH is added? If you look back, our equivalence point was 50 milliliters, right? So I've blown past that. Now I've added another 50 milliliters, okay? So now I'm in that fourth region of the curve. How do I determine the pH here? Okay? So as before, now that we've added some base, right, just like I had to do in regions 2 and 3, right, so now this is after equivalence. I got to account for how much acid-base reaction has occurred, right? So determine how much acid-base reaction has occurred. How have I been doing that? What have I been creating to determine how much acid-base reaction has occurred? Ice table. All right, so let's look at our acid-base equation here. Get rid of my little markings. So I'm going to create an ice table. All right. And for our ice table for titration, since our volume's constantly changing, we're going to have units of what in our ice table? Moles or millimoles. Millimoles are going to be a little bit more convenient because I've been giving you volume in milliliters, but yes, moles of sorts, right? Millimoles is just fine. All right, so in our original problem, we had 250 milliliters, and let's just remember how we do that, right? So milliliters times molarity is what gives us millimoles. So actually, everybody take a second. Our original volume and concentration of our weak acid was 250 milliliters times 0.5 molar. So I had 125. Everybody take a second, given what this problem states, and complete your ice table for your initial concentration of your hydroxide. All right, so that's 250 millimoles. So if I'm going to combine 125 millimoles of weak acid and 250 millimoles of my strong base, how much reaction am I going to see occurring here? How much of that 125 millimoles of weak acid are going to be consumed? All of it, right? Now that's my limiting. I got more base than I need here, so all of that 125 millimoles of weak acid are going to be reacted. And that's as much base as I can have reacted, right? I can't have more base reacting than I have acid. They react in this 1-to-1 ratio. Okay, so now my solution that I'm left over with, I got no more weak acid in there, right? That's all been consumed because I'm past my equivalence point. So now I'm left over with this mixture of strong base and weak base. All right, both of these are bases, right? So both of them will increase my pH, but importantly, the only one that we're going to have to pay attention to in order to calculate our pH is the strong base, because it's going to contribute way, way, way more to that hydroxide concentration than my weak base. This is going to be absolutely negligible compared to my 125 millimoles of actual hydroxide ion. Okay? So the only trick for this region here is that now we can ignore the weak base component and calculate the pH based on the amount of strong base, or OH, we have. All right, so both of these are going to contribute, my strong base and my weak base, but this contribution from my weak base is essentially going to be negligible compared to the contribution from the strong base. So now we can treat this in this region here, just like we did before with our other titration that we looked at. We're going to just treat this as a solution of strong base. Okay, so we need to figure out our hydroxide ion concentration, which is going to be millimoles of OH divided by milliliters of solution. We add 125 millimoles of hydroxide. All right, and looking back on our full problem here, at this point, what is the volume of my solution? It's the 250 that I started with my weak acid, plus the 100 mils that I've added, right? So now I've increased the volume to a total of 350 milliliters. All right, so given that we just determined the hydroxide ion concentration, I want everybody to take a second and calculate the pH of this solution. All right, so I have my hydroxide ion concentration. I can take the negative log of that, but remember that's not going to give me the pH, it's going to give me the pOH. So to find the pH, I have to do 14, minus the pOH. So 14 minus the negative log of that concentration, and I get 13.55 as my pH. Okay, so if we look at our titration curve here, all right. Again, I start out with my solution of weak acid. Then I have this buffer region here where it's pretty resistant to the change in pH, right? I'm adding strong base, adding strong base, adding strong base, but my pH doesn't change very much. More or less plus or minus 1 unit of my pKa. But once I get past that equivalence point, then it just shoots up to being really close to that 14 value there, right? 13.55. Because now, at this point up here, I just have a solution of strong base. All right, so our strategy for this region here, we determine how much acid-base reaction has occurred. Then we're going to determine the pH. But again, our strategy is going to be that we have a strong base solution. All right, so again, I said that these titration problems were really good in the sense that they had us practicing a lot of stuff that we learned how to do in Chapter 17. In Chapter 17, we learned how to calculate the pH of a weak acid, a weak base, a strong acid, a strong base. All of those are practiced within these titration problems, as well as something that we learned first here in Chapter 18, which is calculating the pH of a buffer solution, right? So again, these titration problems are just really good practice. If you know how to do a titration problem, you know how to calculate the pH of a weak acid. You know how to calculate the pH of a weak base. All these things that we should do. Okay, we're going to be done with Chapter 18 this week. So next week is going to be our exam 2 that we have on these two chapters. Going to look the exact same as the first exam, where you're going to have Monday and Tuesday to do that exam. So make sure to have budgeted that time. On Monday morning, we'll come in and we'll try to review as much as possible. All right, but these pH problems these titration problems are a really good way to focus your studying because, again, they just have you practicing so many of the skills that we've learned in these past few weeks. All right, so in addition to these videos that I'll post for what we did in class, there's another video that goes through a worksheet with several titration problems, and then yet another worksheet posted with practice problems for you to do, okay? So again, these are great sort of study tools here, these titration problems, because they just have you doing so much, all right? I know they're long, but again, they got you practicing many different skills, which is great. All right, so now we got to shift our focus to the last aspect of Chapter 18, which is what's called solubility products. All right, so in general, the first semester, you kind of learn about this black and white difference between ionic compounds as being either soluble or insoluble, right? So NaCl is a soluble salt, whereas lead-2 bromide would be classified as insoluble. All right, your world was very black and white at that point. It either is or it isn't, right? However, what we learned about so far in this course was this idea of solubility does have a limit, right? We learned about actually calculating the solubility, or rather using the solubility of, for example, NaCl was something like 45 grams per 100 grams of H2O. Right? So yes, sodium chloride is soluble, but it's not like you can take a dump truck full of sodium chloride and get it to dissolve in a drop of water, right? There is a limit to that solubility. Likewise, when we say insoluble, it's not that it's just like 100% never going to go, all right? There is still some amount, very small, but some amount that will dissolve. And in order to figure out how much that is, we're going to use the KSP of these dissolving reactions. Okay? So for for lead-2 bromide, we're going to create a balanced chemical equation where we put solid lead bromide into solution, and it dissociates into lead ions and 2 bromide ions, right? Balanced chemical equation here. All right, and again, lead-2 bromide is insoluble, so this reaction is not going to go very far in the direction of the products. But again, it's not black and white. We can't just say, nope, this reaction doesn't occur at all, right? And the whole goal of these solubility products is to figure out, okay, well, so how much lead ion do I get when I put this into water? It's not going to be a lot, but it's not going to be zero, okay? And so in order to do that, we need to first build our equilibrium expression for this reaction. So everybody take a second and build me the equilibrium expression for this reaction here. All right, when we're doing our equilibrium expression, what are we going to remember? Products over reactants. So I'm going to put my product, my lead, at my bromide ion. All right, what am I going to do to that concentration of bromide ion? I'm going to square it, because remember, our exponents in our balanced chemical equation, our coefficients in our balanced chemical equation become exponents in our equilibrium expressions. And then am I going to have to include the divided by PbBr2 under there? Why not? Because it's a solid, right? So we only have gases and aqueous solutions that appear in our equilibrium expression, so I don't need that down there at all. Okay, so this is my equilibrium expression for this reaction. Again, these are what are called solubility products, so our K here is KSP. All right, and where do we think we're going to get a value for KSP? Yeah, so we got a constants page with all of these relatively insoluble compounds and their KSP values. And you could see, you could just sort of take a look at these numbers here. They are all very tiny numbers because, again, this reaction does not go very far towards that product side. I don't get very much dissociation, but it's still not nothing. Okay, so our goal is to be able to use these values to figure out just how much of this lead-2 bromide is going to go into solution. All right, so first of all, let's look it up for lead-2 bromide. We got 4.67 times 10 to the negative 6. That's our KSP. Oops. All right, so let's say if 5 grams of lead-2 bromide is added to water, what is the molar solubility of lead-2 bromide? All right, molar solubility is how many moles per liter of PbBr2 will dissociate, right? Will actually dissolve into our solution. What do we think we're going to build to fill in this KSP expression here? Ice table. All right. So we're going to start off with our, let me actually make more room for myself. Okay, PbBr2. Lead ions and bromide ions. Okay. Now, this is one of the weirdest parts about these types of problems. I told you we started out with 5 grams of lead 2 bromide. The result really wouldn't be any different if I started out with 50 grams, if I started out with 0.5 grams, because there's only going to be the teeny tiniest amount that dissociates. So this initial value right here doesn't matter. Okay, you'll actually get the same concentration of lead ions whether you start out with a teeny tiny amount or a large amount. Okay, so it actually doesn't matter how much we start out with. Importantly, though, what's going to happen to the concentration of that lead 2 bromide? Is it going to go up or down? It's going to be consumed. All right? Based on what we learned about equilibrium, having our balanced chemical equation up there, I want you to see if you can fill in this change box here for lead ions and bromide ions. All right, and actually we can be back in concentration here of these ones. What's going to be the change in my lead ion concentration? Plus X. And then what about my bromide ion concentration? Plus 2x. Awesome, right? Because I have this 2 in my balanced chemical equation. So for every 1 lead ion that's created, I'm creating 2 bromide ions. All right, now in my KSP expression, the only thing that I have are these lead and bromide ions. So these two values, my x and my 2x, are the only terms that are going to appear. Okay? This could be something minus x, doesn't really matter. Okay? All right, but we do see that x is our lead 2 bromide being consumed. So importantly, we can make a note that solving for x is our molar solubility. All right, so given our KSP expression, given these equilibrium values here, and given that we figured the value of KSP was 4.67, try to figure out what x would be, our molar solubility. All right, so I'm going to take my lead concentration from my KSP expression. I'm going to plug in x. I'm going to take my bromide ion concentration from my KSP expression and plug in 2x. All right, so that's how I get my KSP equals x times 2x squared. Importantly, that square is applying to both the x and the 2, right? That 2x needs to go into parentheses. It's a really common error for people to say 2x squared. It's the 2x, that whole thing is being squared, right? Concentration of bromide, this whole thing is being squared, and I'm replacing it with 2x, okay? So that 2x is getting squared. This is not it. All right, and so then that equals my 4.67 times 10 to the negative 6. Now I can just do some algebra and figure out what x is. All right, this would simplify to 4x cubed divide both sides by 4. Cancels it out over here. So now I have x cubed equals my KSP divided by 4. And so how am I going to get x? Cube root. All right, now, real quick, cube root, right? So square root, I can almost guarantee you everybody's got a square root button on their calculator. When you're taking a higher order root, sometimes those buttons aren't, I don't know, some calculators have them, some calculators don't. A foolproof way to do it, though, is to raise to a fractional power. So a cube root is the same thing as raising to the power of 1 over 3. So you may have a special square a button on your calculator for higher roots, but one thing that'll work for all calculators is to just take this fractional root here, right? So to be clear, if I'm taking, like, I don't know, something to the root of x, whether it's a cubed root, 4, 5, that's the same thing as y to the 1 over x. Fun with algebra. All right, and so what I get is my molar solubility is 0.0105 molar. All right, again, these higher order roots can be kind of weird. If you're having trouble punching it into your calculator, please make sure to see me afterwards and we can figure it out for your particular calculator. All right, so that's how you would figure it out if I asked you for the molar solubility. What if I said, what is the concentration of bromide ion? All right, well, let's look at all this work that we've done. We figured out what X is, our molar solubility. How could I use that to find my bromide ion concentration? What is the bromide ion concentration at equilibrium? 2x. Okay, so if I wanted to know specifically that bromide ion concentration, I would just take X and multiply it by 2. Right? Because for every mole of lead bromide that dissociates, I get 2 moles of bromide. So this would be 2 times X, which is just 0.021. All right, so let's practice this again. Let's do another one from scratch here, all right? Go to our, let me pick one of these compounds here. Whoops. We're going to do this business. Lanthanum iodate. All right, and we want to find what is the molar solubility of this lanthanum iodate. All right, so first give me that solubility product. Balanced chemical equation. All right, so I'm going to take my solid lanthanum iodate. That's going to dissociate into these lanthanum ions, as well as iodate ions. And everybody take a second to balance this chemical equation, because we're not going to be able to use it unless it's balanced. Once you've got it balanced, you're going to give me that KSP expression. And once you've got your KSP expression, you're going to build that ice table. All right, so I got my KSP expression, right? I got to cube that iodate ion concentration since there's a 3 in my balanced chemical equation. I'm going to fill out my ice table. Again, one of the weirder parts of this problem is it actually doesn't matter how much that you start out with because we're just going to get such a tiny number for x anyway. Okay? Importantly, I decrease my amount, my original solid, and then I'm going to increase my products. What should go in this box? Just plus x, because there's a 1 in my balanced chemical equation, but in the iodate column should be plus 3x, because there's a 3 in my balanced chemical equation. All right, so x and 3x. And then again, this is kind of where it's the easiest to make a mistake is now we're going to plug these values in to our KSP expression. Right? Lanthanum concentration is going to be replaced with x. Iodate concentration with 3x. So I'm going to get KSP equals x. And then in parentheses, 3x cubed. Right? That 3 also needs to be cubed. All right? By far the easiest place to make a mistake. And that equals that value that we looked up, 7.5 times 10 to the negative 12. Now I can just do some algebra. 3 cubed, 3 times 3 times 3 is 27. X cubed times x is x to the 4th. So 27x to the 4th equals 7.50 times 10 to the negative 12. I'm going to rearrange by dividing both sides by 27. That cancels it out over here. So now I'm left with x to the 4th equals 7.5 times 10 to the negative 12 divided by 27. And I'm going to get rid of that by taking the 4th root. Again, we can do the same thing by raising it to the power of 1/4. That'll work in anybody's calculator. All right, so again, we solve for x to get our molar solubility. Did I do this right? Get 0.000729. I guess we're not going to pay attention. We'll say 3 sig figs. Sure. All right, so when we solve for x, we get our molar solubility. So then the next thing that I could ask you would be something like, okay, now what's the concentration of the iodate ion? And how do we find that concentration? Where are we going to look? Our ice table. And what our ice table tells us is that our iodate concentration at equilibrium is 3x. So I'll just take my molar solubility, multiply it by 3. Right? So 3x equals 0.002178. We'll say 3 sig figs again. All right, and I guess I can be good and say our units here for our ice table are concentration. All right, so these are these molar solubility problems. We're going to take a compound that we would classify as insoluble. I mean, 0.00218 is a really tiny concentration, right? Not very much of this dissolves at all. But we can use our equilibrium expression to figure out just how much does dissolve, okay? You know, why is this important? Like for our previous example, lead-2 bromide, right? We didn't get very much lead in solution, but lead is absolutely terrible for you, right? So you want to know, even if there's a tiny, tiny concentration, that could be significant, right? So for something like lead or arsenic, these could very much so matter, all right? Cool.